Welcome you all for the week 1 lecture 3 CDT3, that is analysis of continuous beam without sinking of supports. Analysis of continuous beam without sinking of supports. So this is myself, S. Rajshekhar, Assistant Professor of Department of Civil Engineering, Kitshwaram. So now we'll see the lecture outcomes. After completion of this lecture, the student will be able to calculate the fixed end moments due to different loading, and also student will be able to analyze the continuous beams by using slope deflection method of analysis. The first lecture outcome is student will be able to calculate the fixed end moments for different loading, and student will be able to analyze the continuous beams by using slope deflection method of analysis. Yeah. So for this, I'm taking a problem, analysis of continuous beam problem. So this is two span continuous beam, span AB and span BC. The both ends, extreme ends of the continuous beams are fixed. At B, a roller support is there. At A, fixed support. At B, at C, fixed support, and at B, roller support is there. And it's here for this beam, AB beam, it is I, and for BC beam, it is 12. Inertia is, that is a moment of inertia is 12. For AB span, a point load, that is a concentrated load of 40 kilonewtons is acting at the center of the AB beam, and a uniform distributed load of 20 kilonewton per meter is acting for the BC span. So now he's asking to in this problem we need to analyze this continuous beam by using slope deflection method of analysis, and also draw the bending moment diagram and shear force diagrams. And also draw the elastic curve. And also draw the elastic curve, and he's saying that Young's modulus is same for all vectors. So throughout this continuous beam, Young's modulus is same throughout the continuous beam. That is E is constant. So this is the given problem. For this given problem, we want to solve by using a slope deflection method of analysis. The first thing what we need to do is we have to observe what is the type of load it is. So we have two types of loads is a point load and a uniform distributed load. Okay. So for the calculation of final end moment by using moment slope deflection method of analysis, as I told you in the previous classes, so total end moment due to final end moment is due to, first one is due to loading, second one is due to settlement of support settlement, that is I'm just denoting that is delta, and the rotation of support. So if you observe at support A, rotation is 0, that is theta A is equal to 0. At support B, theta B will be there, that is unknown, that we need to calculate. At support C, theta C is equal to 0. So slope deflection method is a displacement method. As I told you in the beginning classes, in the slope deflection, in the displacement methods, the basic unknowns are the displacements. Basic unknowns are the displacements. So here the unknown is theta B. First we have to calculate the theta B, displacement theta B, that we need to calculate first. So here settlement is not there, settlement of support is not there, only rotation is there. Only rotation is there, the slope is there, displacement is not there, settlement of support is not there. So delta will be equal to 0 for all the spans. Only theta B is unknown, theta A is 0, theta C is 0. Why? Because this fixed support, for the fixed support, theta A is 0, delta 0. For roller support, delta will be 0 and theta will be there. That is rotation will be there. For the support, rotation theta B will be there. That we need to calculate that rotation. Okay, that's it. So for this, so theta is not there, only theta will be there, delta is equal to 0. That means final end moment we can calculate. Final end moment is due to only loading as well as rotations. Okay, so now what we have to do is we have to calculate this theta b. So for the calculation of theta b, we have to use some equilibrium equations. Compatibility conditions we will use. Okay, right. First of all, I want to calculate moment due to loading. Step one. So as I told you, final and end moment will be equal to due to loading, due to settlement of support, due to rotation. So first I want to calculate moment due to loading, fixed end moment due to loading. Because of the application of load, that load is transferred to the supports. Whatever the load we are applying here, that is transferred to the supports. So after because of this transformation, a reaction will going to develop at the supports. Resisting moment will going to develop at the support. Resisting moment will going to develop at the supports. At A, we have a resisting moment. At B, we have a resisting moment. For the AB span, we have two resisting moments. For BC span, we have two resisting moments. Okay, right. Those the resisting moment is due to loading, due to settlement of support, due to rotation of the support. So now, first I want to calculate the moment due to loading. End moment due to loading. So end moment due to loading. So we are given formulas for the calculation of end moment due to loading in the previous class, in the previous lecture. Fixed beam subjected to point load at center. Then for the calculation of fixed end moments, MFAB and let's say this is A and this is B. MFAB will be equal to minus WL by 8 or PL by 8. WL by 8, MFAB will be equal to WL by 8. MFBA will be equal to plus WL by 8. So this is producing clockwise resisting moment. Here it is anti-clockwise resisting moment. So clockwise resisting moment will be considered to be positive, that is positive WL by 8. So for this P, fixed moment will be moment due to loading. Moment due to loading is minus WL by 8 for the AB span for at A plus WL by 8 at B for the span AB. Okay, for the span AB. So first of all, I want to calculate MFAB for this one. AB span MFAB will be equal to minus WL by 8. MFAB equal to minus WL by 8. That is, we are getting W value is 40 kilonewton, L value 4. For WL by 8, if you calculate it, you are going to get minus 20 kilonewton meter. Similarly, if you calculate MFBA, the intensity is same, magnitude is same, but plus WL by 8 now. So magnitude is same, but sign is different, plus WL by 8. So 20 kilonewton meter. So now coming to BC span, the fixed end moment can be calculated as WL square by 12. Fixed end moment due to loading will be equal to WL square by 12. So this is MF BC will be equal to minus WL square by 12. So this is this one. We substitute W is equal to 20 kilonewton per meter and L value 6. You will going to get minus 60 kilonewton meter. Calculate MFCB also. MFCB is equal to MFCB, fixed end moment due to loading. MFCB will be equal to the formula here we have plus WL square by 12 plus WL square by 12. That is, we are getting plus 60 kilonewton meter. Plus 60 kilonewton meter. So we are getting moments due to loading. Okay, so total we have three types of moments will going to develop at the supports. First one is due to loading, second one is due to settlement of support, third one is due to rotation of the support. Okay, so fixed moment due to loading that we are calculated. So we have to add this to the rotation of support. We need to add rotation of support plus settlement of support. If more it add yes, we're going to get the final moment. Okay, now we'll go to the steps 2. For the calculation of rotation, the slope deflection method of design, we need to form slope deflection equations. We need to develop slope deflection equations. So right, we'll see the slope deflection equations for the span AB. For the span AB, let us say this is the AB span. This is A, support A, and this is support B. For AB span, MEAB, final end moment MEAB will be equal to MFAB plus 2A by L into 2 theta A plus theta B, 2 theta A plus theta B minus 3 delta by L. MEAB final end moment will be equal to moment due to loading, that is fixed end moment, plus 2EI by L into 2 theta A plus theta B minus 3 delta by L. So this is the equation. Similarly, MFAB, this is MFAB. MEAB will be equal to, this is the equation. Now MBA will be equal to MBA will be equal to MFBA plus 2EI by L into 2 theta B plus theta A. Theta B plus theta A minus 3 delta by L. Minus 3 delta by L. So that is the two equations we'll use for the development of slope deflection equation. So first one, if you see AB span, theta A is equal to 0. To take AB span, theta A is equal to 0. Theta B is unknown. Only theta B. So substitute in this equation MEAB 2EI by L plus 2 theta A plus theta B minus 3 delta by L. So theta A is 0. So theta A is 0. Okay. Theta B is unknown. Delta is also 0. So simply we can write 2 EI by L into, so I will write here for the AB span, I will write here. For AB span, this is a span, I'll draw here. This is uniform distributed load and this is point load. A, B, C. So for AB span, theta B is the unknown. Theta B is equal to unknown. Theta A is equal to 0. Substitute this. Theta A is equal to 0. Theta B is equal to 0. And delta is equal to 0 in this equation. That is MEAB is equal to MFAB plus 2EI by L, 2 theta A plus theta B minus 3 delta by L. Substitute M. So theta is equal to 0. Delta equal to 0. Only theta B is the unknown. Theta B untadi, and EI is equal to E value constant, I value I for AB span, I value 2I for BC span. Okay. And fixed end moment MFAB is minus 20. MFAB fixed end moment due to loading, that is MFAB is equal to minus 20. MFAB is equal to minus 20. That you have to substitute here. You consider this is equation number 1. So now we are getting MEAB will be equal to this equation we are getting. MEAB equation we are getting here. So 0.5 EI theta B minus 20. Okay, theta B minus 20 we are getting. I am just considering this is equation number 1. Now similarly, you write the equation for MBA, the same span but different direction. Same span, AB span, but BA direction. Direction is BA. MBA will be equal to this formula we need to use. MFBA plus 2A by L 2 theta B. Here only thing is for theta B factor will be 2. For theta A factor will be 1. So 2 theta B plus theta A minus 3 delta by L. 2 EI by L. L is equal to 4 meters. For the span is 4 meters. Into theta A plus 2 theta B minus. So theta A is equal to 0 as we know. Support A is fixed support. For fixed support theta A is equal to 0. So theta B is unknown. Delta will be 0. And MFBA will be equal to plus 20. MFBA. Just now we are seeing MFBA. MFBA is equal to plus 20. MFBA. We are calculated, that is fixed moment due to loading. That is MFBA is equal to plus 20. MFBA is equal to plus 20. So this is consider equation number 2. This is equation number 1. This is equation number 2. Similarly, you write equation MFBC as well as MFBC as well as MFCB. This is equation number 4. Equation number 3. This is equation number 3, MFBC, and equation number 4. Similarly, you write for MFBC and as well as MFCB. So we got 4 equations. All are in terms of theta b. All are in terms of theta b. Okay. So now we have to solve for. We need to solve theta b. So for that, we have to use compatibility conditions, additional equilibrium equations we have to use. That is, we know that equilibrium equation, another equilibrium equation is joint equilibrium equation. Joint equilibrium equation. That is, the summation of moments at the joint will be equal to 0. Summation of joint, this is support A and this is support B and this is support C. Summation of moment at the joint must be equal to 0. At joint we have two moments, MBA, and in this direction we have another moment, that is MBC. So from the joint equilibrium equation, so this is a roller support. It is this roller support, summation of moments must be equal to 0. At the moment, sum of the moments at the roller support must be equal to 0. The condition. So at the joint must be equal to 0. That is MBA plus MBC will be equal to 0. This is the condition. Because the roller support will not take any moment. The sum will be equal to, summation of moments will be equal to 0. MBA plus MBC equal to 0 on condition. The equilibrium equation. So substitute MBA. Just now we have calculated MBA. MBA is equal to, this is the MBA. MBC, so this is MBC. If you add MBA plus MBC equal to 0, then you are going to get the theta b value. You are going to get the theta b value. So theta b, EI theta b we are getting. EI theta b is equal to 17.143 radians we are getting. Now you substitute theta EI theta b value in the equation MAB, MBA. So MAB equation, MAB, MBA, MBC, MCB. You substitute in those 1, 2, 3, 4 equations, you will go into final end moments. MAB is equal to minus 14.428 kilometer meter. MBA is equal to 37.143 kilometer meter. MBC will be equal to minus 37.143 kilometer meter, and MCB is equal to 71.429 kilometer meter. So like that, we will going to calculate the final end moments. So this is the slope deflection method. Like that, we will going to analyze slope. Okay. Yeah. Students, we will see the shear force diagrams, bending moment diagram in a separate session. Separate video I will make for the drawing of slope. There is a shear force diagram and bending moment diagram. In detail, we need to discuss. So for that, I want to make a separate video for this. So I'm just concluding this. So this is a lecture level practice problem. The same thing. The only difference is here it is fixed support, but it is roller support. The only difference. Okay. Only thing you need to solve. So thank you, one and all.